Good morning. Today we are going to dive into a world of micromolecular synthesis, the elegant chemistry that turns simple molecules into the fundamental building blocks of modern materials. Whether we realize it or not, we live in a polymer dominated world, from the DNA encoding our genetic blueprint to the advanced synthetic fibers in high performance gear. Polymers are everywhere. Over the next 10 minutes, we will unpack how these giant molecules are constructed, the specific mechanics that drive their growth, and the industrial impact they carry globally. Let's begin by looking at the basic nature of polymer. The nature of polymer. If you look at the 3D molecular render on the left, you can see what looks like a long repeating chain. This is the visual definition of a polymer. The word itself comes from the Greek poly, meaning many, and meros, meaning parts. At its simplest, a polymer is a giant molecule made by linking hundreds of thousands of molecules, repeating units called monomers. Monomers. Think of monomers as individual paper clips and the polymerization reaction as the process of hooking them together to make a long chain. The chemical bonds that hold these chains together are strong covalent bonds. Because these structures are so massive, they possess unique physical behavior like elasticity, toughness, and thermal resistance that small molecules simply cannot duplicate. We generally classify polymers into three structural architectures. First, on the left, we have linear polymers. Here, the monomer units are joined in straight, continuous chains. Because they are straight, they can pack tightly together almost like uncooked spaghetti in a box. This tight packing gives them high density and high tensile strength. A common example is HDPE, which is used to make rigid milk jugs. Next, the middle are branched polymers. Here, slight chains branch off the main backbone. This branching prevents the molecule from packing tightly together, resulting in lower density, more flexible material such as LPDE, which is what plastic grocery bags and squeeze bottle are made up of. Finally, on the right, we have cross-linked network polymers. In this case, individual chains are chemically linked together by covalent bonds to form a robust three-dimensional grid. These are thermosetting plastics. Once they cure, they cannot be melted or reshaped because the crosslink hold them permanently in place. Materials like bakelite or vulcanized rubber are classic examples. The two core pathways. Now that we understand the structure, how do we actually synthesize these materials? These are two primary synthetic pathways in polymerization: addition and condensation. On the left, we have addition polymerization, also commonly referred to as chain growth. In this process, monomer containing double or triple carbon carbon bonds, like alkenes, rapidly attach to an active center on a growing chain. A key detail to remember here is atom efficiency. Absolutely no atom are lost in this reaction. The polymer contains 100% of the atoms of the starting monomer. On the right, we have condensation polymerization or step growth. In this pathway, monomer with reactive functional group on both ends couple together slowly. Every single time two monomers join, a small byproduct molecule, mostly commonly water, hydraulic acid, or ammonia, is expelled or condensed. Because of this, the final monomers because of this, the final polymer molecular formula is slightly different from the starting monomer. Now, we are going to see addition mechanism. Let's zoom in on the exact step of the addition mechanism. This process is incredibly rapid and happens in four distinct, highly controlled kinetic phases. Phase 1 is initiation. It begins with highly reactive initiator such as free radical, cation or anion that attacks the double bond of a monomer, generating an active reactive center. Phase 2 is propagation. This is the growth phase. The active center on the monomer rapidly attacks on neighboring monomer, opening its double bond and transferring the active site to the end of the new link. This chain reaction repeats thousands of times in the fraction of a second, causing the chain to grow exponentially. Phase 3 is chain transfer. Sometimes the active radical site gets accidentally transferred a solvent molecule, an initiator, or even another polymer chain. This effectively stops the growth of the original chain but starts a new one. And finally, phase 4 is termination. This occurs when two active growing chains collide and combine their reactive ends, or when they undergo disproportion. This permanently neutralizes the active site, resulting in stable, complicated polymer chain. This graph perfectly illustrates the kinetic difference we just discussed. Here we have molecular weight on y-axis plotted against the percentage of reaction conversion on the x-axis. Take a look at the slide at the solid teal line representing chain growth or addition. You can see that even at incredibly low conversion rate, say 10% or 20%, the molecular weight of polymer species present is already near its maximum. This is because once a chain is initiated, it propagates to full length in milliseconds before terminating. Now, contrast that with the dark dashed line representing step growth or condensation. The line stays flat on the bottom or almost the entire reaction. At 50% or even 80% conversion, you mostly have short dimers, trimers, and oligomers. It is only in the final moments of the reaction, as we approach 98% to 100% conversion, that these oligomers finally couple together to create the steep exponential peak in molecular weight. For material scientists, understanding this graph is crucial. If a step growth reaction is stopped even slightly too early, the resulting material will be brittle and useless because the chains aren't long enough yet. Where do these chemistry paths end up in real world? This global portion chart shows the distribution of synthetic polymer production. You will immediately notice that addition polymer dominate the global market. Polyethylenes make up 38% of global production, followed closely by polypropylene at 25% and polyvinyl chloride at 18%. Combined, these three families of addition polymer represents over 80% of the world's synthetic polymer. They form the backbone of our packaging, infrastructure, piping, and medical supplies due to their cheap synthesis and highly tenable physical structure. To conclude, the study of polymerization is not just about making plastic, it is about designing molecules with intent. As we move in future, the focus is shifting from simple high volume synthesis to creating advanced smart materials like biodegradable polymers, self-healing networks, and circular polymers designed to be chemically recycled back into their original monomers. Thank you very much for your time and attention today. I would now like to open the floor to any question you might have about polymerization, kinetics, structural classification, or the synthetic pathways.